Alright, we're back. Today we're looking at 7.1 problem number 10. 7.1 problem number 10. And this has to do with basically logarithm defined as an integral and Euler's constant, exponential function also. In this case, though, this problem's rather weird because 7.2 is a differential equations. But this is an initial value problem, which I could argue is pretty much the same thing as a separatable differential equation. So you may want to watch my differential equation separable video before following through this one. Anyhow, the first step we're going to do is we're going to move the dt over here by multiplying it on both sides. Now that's not official. There's a more mathematically precise way to do it, but this will work for you to get the correct answer, and it's a little more straightforward. So as long as I leave you with that disclaimer, know that you can use it and it'll work, but there is a more proper way to do it. Alright, so now we got all of our y's, which there were none, on the dy side, and all of our t's, which there were a lot of t's, on the dt side, and in doing so we've separated our variables from each other. Well, now we can throw up the old integral bars, and this side's not too bad. The integral of 1 dy is just y, so y equals whatever this one is, which is going to take a little bit of work. So the first thing I do when I'm searching for a u substitution is I usually look for something that will help me eliminate something on the outside of that substitution. So, for example, my eye is drawn through intuition to this statement here, because if I take the derivative of this statement, I'll end up with 4e to the 4t as my derivative. And here's my 4e to the 4t. So I'm going to go ahead and let this equal u. And so if u equals e to the 4t minus 625, then du dt equals 4e to the 4t, and then of course minus nothing because the derivative of a constant is 0. Now I can likewise incorrectly multiply both sides by dt. It'll work, but it's not necessarily mathematically rigorous. And so now at this point I've got a substitution for du, and if you'll take a look here, my du can take care of this statement right here, and my u can take care of this statement. And when I go ahead and do that substitution, I'll find that y equals the integral of sine of u du, right? Because du took care of 4e to the 4t dt, or yeah, it took care of these parts of the problem, and then the u is inside the sine, so the sine still remains. But now we know how to take the derivative of sine. It would be cosine, but we're going backwards. Antiderivative of sine is negative cosine of u. Don't forget the plus c, because derivatives, when you take derivatives, you destroy information that would allow you to pin where you're at. For example, if I had, let's say I have 3 different graphs, and they have the same slope at every given point. So they have the exact same slope for every x value, therefore their derivatives are the same. But that's a problem when we're taking the integral, because what that means is that when we take the antiderivative, all we know is the slope, the shape of the graph, but we don't actually know where it's pinned at. And so the plus c will be different for every problem, and that plus c will show you how much you shifted vertically to make this specific function. And that's why we're given an initial value here. They tell us that y of ln of 5 equals 0, which is going to help us solve for c. And that's going to allow us to pin the tail on the donkey, so to speak. Next step here, we've got this set equal to y. We're not interested in u, we're interested in y and x. Or, I'm sorry, we're interested in y and t. So let's go ahead and substitute what u is in terms of t back in. So negative cosine of u, which is equal to e to the 4t minus 625 plus c equals y. Well, now I can use my initial value. As you can see here, I'm plugging in ln of 5 to my y formula. And what this means is that my x, I'm plugging in ln of 5. See, y is a function of x, so when x is ln of 5, my output, which is my y function, is equal to 0. So I can go ahead and make these substitutions, and that's going to set 0 equal to minus cosine of e, oh, and I'm sorry, this is t. I keep screwing that up. Our independent variable here is t. When we plug in ln of 5 to y, we get out 0. Plug in ln of 5 to the function that's in terms of t, and we get out 0. So 4 times t, well, t is ln of 5, minus 625 plus c, all equals 0. Well, if you remember, there's something called the power rule of exponentials and logarithms, where I can actually take this 4, and I can write it up here. So I can take it from the front of the log and move it up into a power position. And then I can take 5 to the power of 4, which gives me 625. So this is in fact e to the ln of 625. Well, exponentials and natural logarithms are inverses of each other. They're inverse functions, and so they'll cancel out. And what you're left with here is 625 minus 625, all inside this negative cosine, plus some c is equal to 0. Well, 625 minus 625 is 0. Cosine of 0 is 1, but this is negative cosine. So negative cosine of 0 equals negative 1, plus c equals 0. Well, now we can finish it off and solve for c. So c must equal 1 in order for this expression to be true. There we go. So yeah, we just add the 1 over here, we find c is equal to plus 1. Then we can go back to this step right here, where we have the differential equation written out in terms of t, and we can plug in the vertical shifter that we found, which was 1. So this is our answer to our initial condition problem, or I think they call it, yeah, this is the solution to our initial value problem. And remember, this adding constant over here just tells you where your graph is at. The curve of the graph is the same, but there's infinitely many curves that are possible. So what this initial value does is it takes all those infinitely many curves and it tells you that there's only one that it works with. And this one happens to be the one that this initial value problem works with. So I hope this was helpful, and I'll see you next video.